Hi everyone. Now I am going to discuss about the phase rule and its application. Before discussing the phase rule, you should know some important terms involved in a phase rule. So that will be the different topic. So what are the terms involved in the phase rule and what are the examples? Now I am going to discuss two component system. So one component system will be discussed by the Dr. Rajagopalan sir. So I am going to explain the two component system. There are many compounds existing in a two component system. There are many examples for two component system. So in our syllabus, we are having a lead silver system. Before discussing the lead silver system, so let me have a general overview about the important terms. Because by understanding the terms involved in the phase rule, then you can easily understand how the phase diagram is constructed. Okay, let's see. So this is a topic we are going to discuss now. Phase rule for two component system. So before discussing the two component system, some important terms. So I'm not going to elaborate the terms. Shortly, I will tell what are the important terms. The first term is what is meant by phase. Second term, component. Third term, number of degrees of freedom. The fourth term, that is a phase rule. Fourth term is phase rule, and the last one is condensed phase rule, or the condensed phase rule is otherwise called as reduced phase rule. The condensed phase rule, reduced phase rule. So now we will have an overview about these basic terms, because for understanding the construction of a two component system, for understanding the construction of a lead silver system, so you should know what is these things. So by understanding these things only, you can easily understand about the two component system. The first one is a phase. Phase. Now it is a question, what is phase? Phase is a homogeneous, physically distinct and mechanically separable portion which have a definite boundary. So let's see the example. So I'm having a marker in my hand. So it is a physically distinct and it can be mechanically separable and it has a definite boundary and it is a homogeneous because it is in a solid state. So there are three different states. Solid, it is a well-known thing, a basic thing. Solid, liquid and gaseous state. And the example what I have taken now is marker. It is a solid state, homogeneous, we can see it, physically distinct and mechanically separable portion, and it have the definite boundary. So this marker is having a definite boundary. So this is called a phase. So phase is a homogeneous, physically distinct, mechanically separable portion. So let me take one example. You can take water. The molecular formula of water is H2O. The molecular formula of water is a H2O. It can exist in three different phases. So it can exist in a gaseous phase. The gaseous phase is a water vapor. And it also exists in a liquid phase. The liquid phase is called as a water. And it can exist in a solid phase and it is called as ice. So the molecule H2O exists in three different phases: solid, liquid, gas, which are called as ice, water, vapor respectively. So this is example for one phase. So this is example. In examination, sometimes they may ask to detect the number of phases. Usually they will ask to detect the number of degrees of freedom. Sometimes they will ask to detect the number of phases. So for that, you should have a good idea about how to differentiate the one phase from another phase. For example, the question may be, find out the number of phase or phases in the following equilibrium reactions. In the following equilibrium reactions. So this is a basic thing. Usually you will get you will be asked to find out the number of degrees of freedom. Sometimes you will ask to find out the number of phases also. So I will write out one or two examples. The equilibrium reaction may be the ice is equilibrium with water. So this is one of the equilibrium reaction. So ice is equilibrium with the water. Another question is, how many number of phase present in this equilibrium? So ice is present in a solid state, water is present in a liquid state. So the total number of phases present in this equilibrium is equal to 2. The total number of phases present in this reaction, which is equal to 2. Okay, we'll move to the next one. The next term, what we are going to discuss is component. The term 2 is component. The definition of component is the minimum number of chemical constituents required to define the system. The minimum number of chemical constituent is required to define the system. If I will explain the example, it is easy to understand the definition of a component. Without explaining the example, it is a little bit tough to follow. So I will write one example, a decomposition of a calcium carbonate. Calcium carbonate is solid material. During the decomposition, while heating, it can be decomposed as calcium oxide. Calcium oxide is also the solid material and it will emit a carbon dioxide. Now, we need to find out the number of components present in this reaction. Now, we can come to the definition of a component. It is the minimum number of chemical constituents required to define the system. Now, the question is, how many number of chemical constituents are required to define the system? How many number of chemical constituents are required to define the system? So, the answer is 2. I will tell how the answer is 2. The first component is calcium oxide. The second component is carbon dioxide. Now the question may arise, sir, it contains 3 different chemical constituents. Am I right? The first one is a calcium carbonate, calcium oxide, carbon dioxide. So these are 3 different chemical constituents present here. But you are saying the number of components present in this equilibrium reaction is 2. How? That is the question. Now you need to clearly understand the definition. It is the minimum number of chemical constituents. Minimum number of chemical constituents means, so let us consider 1 calcium oxide and 1 carbon dioxide is out there, means by combining these two, we can get calcium carbonate, which means by using these chemical constituents, we can explain the calcium carbonate. And without a calcium oxide, without zero calcium oxide, without calcium oxide, 1 carbon dioxide is there. So we can explain. So we can explain the phase carbon dioxide. Meanwhile, without a carbon dioxide, by taking a calcium oxide alone, zero carbon dioxide. So we can explain the calcium oxide. So I have taken only the two phases. This is the first one and this is the second one. By using these two chemical constituents, I have explained the all three phases which is present in the reaction. So the number of chemical constituents which is present in the equilibrium reaction is called as a component. So for this equilibrium reaction, the component is equal to 2. So what are the components? Number 1 is calcium oxide, number 2 is a carbon dioxide. So these are the two chemical components required to define this equilibrium reaction. So these are basic terms about the chemical component. Okay, we'll move to the next one. The third thing is number of degrees of freedom. Number of degrees of freedom. The third term is number of degrees of freedom. Number of degrees of freedom. So if you want to mug up the definition, if you mug up the earlier the component definition of the component, means it is easy to remember the number of degrees of freedom. What is a component? Minimum number of chemical constituents required to define the system. Here, number of degrees of freedom is minimum number of independent variables required to define the system. The answer is minimum number of independent variables are required to define the system. Usually, in your question paper, in your examination, you will get a problem like to calculate the number of degrees of freedom. How can you calculate the number of degrees of freedom? It can be calculated by using a phase rule. Now I'll explain the phase rule and then I will tell how to calculate the number of degrees of freedom. So the phase rule is, just you can leave it here. Now you can come to the next one, that is a phase rule. Phase rule is simple equation. By using a simple equation, you can easily define the phase rule. That is F equal to C minus P plus 2. F equal to C minus P plus 2. So what is F? What is C? What is P? Already we have listed here. P is a phase. Phase is abbreviated as a P. Component is abbreviated as C. Number of degrees of freedom is abbreviated as F. So now we have the expansion for all the things. F is a number of degrees of freedom, number of degrees of freedom. C is a component, P is a phase. Now the question may arise, sir, what is mean by the number 2? So these number 2 represents, the number 2 represents two variables. The variables are temperature and pressure. The two variables are, first variable is a temperature and the second variable is a pressure. So this is the phase rule. Now you can clearly understand the phase rule. That is a simple equation, F equal to C minus P plus 2. F is a number of degrees of freedom, P is a phase, C is a component. The number 2, which is present in a phase rule, represents the two variable. The first one is a temperature and second one is a pressure. Now we can come to the finding out the number of degrees of freedom. The number of degrees of freedom is determined by using a phase rule. I'll tell you the example. The same example what we have taken to calculate the previous component. Now we will take the decomposition of a calcium carbonate. We will go from the simple example. Before discussing the decomposition of a calcium carbonate, I will tell you the simple example and then move to the some more complicated. I can imagine the equilibrium between the water with water vapor. Water with water vapor. So this is the equilibrium reaction. Equilibrium reaction is water is equilibrium with the water vapor. So for this equilibrium reaction, we need to find out the number of degrees of freedom. To find out the number of degrees of freedom, we need to use a phase rule formula. Already we have discussed the phase rule formula. So this is the formula. This formula I am going to apply to calculate the number of degrees of freedom in this equilibrium reaction. Let me calculate. So the formula is F equal to C minus P plus 2. F equal to C minus P plus 2. We need the F value. So we should find out what is the value of a C and what is the value of P. C is component. The definition of component is minimum number of chemical constituents required to define the system. So what is the C? What is the chemical constituent? What is the molecular formula of water? The molecular formula of water is H2O. And what about the molecular formula of water vapor? Same. So the molecular formula of water, the molecular formula of ice, the molecular formula of water vapor. So everything will be the same. It is a one component system. Water is example for one component system. So the number of component is 1. What is the component? H2O. Here also it will be exist as a H2O. Here also it will be exist as a H2O. So the component is 1. And the next number of phase. How many phases present in this equilibrium? Water is an example for the liquid phase. The phase number 1 is liquid. Phase number 2 is a gas. Water vapor is present in a gaseous state. So the total number of phases present in this equilibrium reaction is 2. So phase is equal to 2. Now we have determined the number of component phases present in this reaction. Now just substitute these value in the phase rule formula, we can get the answer. That is F equal to 1 minus 2 plus 2. F equal to 1 minus 2 plus 2. The answer F equal to 1. So the number of degrees of freedom in this equilibrium reaction is 1. So this is a simple one. This is simple one. Now we can see the example. How to find out the number of degrees of freedom for a decomposition of calcium carbonate equation. So this is a basic and simple, a little what complicated. This is to find out the number of degrees of freedom of a calcium decomposition of a calcium carbonate. The molecular formula of a calcium carbonate is CaCO3 and it is decomposed and it forms a calcium oxide and carbon dioxide. Now the question, find out the number of degrees of freedom in this equilibrium reaction. Sometimes in exam paper itself you will get the what are the phases, nature of the phases in a question paper itself. Calcium carbonate is a solid, calcium oxide is a solid and carbon dioxide is a gas. The formula to find out the number of degrees of freedom, F equal to C minus P plus 2. Our first job is we need to find out the number of component and number of phases. Okay, component. While discussing the component, already I have explained how to find out the number of component for this equilibrium reaction. That is a minimum number of chemical constituents required to define the system is 2, which are one is calcium oxide, number 2 is a carbon dioxide. So the component present in the equilibrium reaction is 2. And phase. Now one new concept I am going to explain here. See how many number of phases are present. Solid, gas. So in general, it is a 2. One is a solid, another one is a gas. This is a solid, this is solid. So solid, single phase. The second one is gas. But the answer, if you tell it as a number of phases are 2 means the answer is wrong. The reason is solids are immiscible. Solids are immiscible. So if more than one solid or if many solid present in the equilibrium reaction means that will be considered as separate phases. See, for example, so I have this marker and the cork and the marker. So this is a one phase, this is another, this is a solid, this is solid. So I cannot mix the both phase. I cannot mix these both phase. So it will exist as a separate phase, it will exist as a separate phase. It may possible, the mixing may possible when the material is heated at very high temperature. At very high temperature, the material can be converted into the molten state. So at the molten state may possible, but at the room temperature, so if the n number of solids are there means it will be considered as a n number of phases. So phase number 1, phase number 2, phase number 3. Number of phases are 3. Now you need to apply the, substitute the values in the phase rule formula. F equal to, component is 2, phase is 3 and 2. So F equal to 2 minus 2 plus 2, what you will get? 4 minus 3, it is a 1. So the number of degrees of freedom for this equilibrium reaction is 1. If the number of degrees of freedom is 1 means the system will be called as a univariant. If it is a 2 bivariant. If it is a 0, it is called as a non-variant. So this is about the number of degrees of freedom. So remaining one concept we are having. The key thing is the condensed phase rule or the reduced phase rule is applicable for metal alloy system. So what we have discussed so far is in general phase rule we have discussed. This phase rule is applicable for a one component system. So that will be discussed by the Dr. Rajagopalan sir in the lecture, in a previous lecture. But the reduced phase rule will be applicable for two component system, which I am going to explain here. So you need to carefully listen what is meant by the reduced phase rule. There is not a much difference between the phase rule and the reduced phase rule. Simple modification of phase rule. The name itself having the meaning. What is the phase rule? Just I can recall the phase rule. Now I am going to explain the number 5. Reduced phase rule. Reduced phase rule. Reduced phase rule. What is a phase rule? Will come from the phase rule itself. F equal to C minus P plus 2. This is a not reduced phase rule. This is a phase rule. Now this will become reduced. How it will become reduced, sir? See, the number 2 represents the two variables. I already told. The number 2 represents the one variable is a temperature, another variable is a pressure. There are two variables present in this equation. In the case of a metal alloy system, if you heat the water, what will happen? Just you can take can start from the ice at 0 degree centigrade. H2O is existing as ice. When the ice is heated, what will happen? It will be melted and it will be converted into water. Further heating of water, what will happen? Above 100 degrees centigrade, the water will be converted into the water vapor. So this is a scenario for a water system. And what will happen while heating the metal alloy system? For example, next we are going to discuss the lead silver system. In case if you're taking the mixture of a lead and silver, if you are taking in a vessel and you are heating the lead and silver, what will happen? At a somewhat around 327 degrees centigrade, lead will be converted into the molten state, because the melting point of a lead is at 327 degrees centigrade. At a 961 degrees centigrade, silver will be converted into molten state. Further heating, what will happen? Further heating at 1000 degrees centigrade, at 1500 degrees centigrade, or at 2000 degrees centigrade, what will happen? Nothing will happen. It will exist in a molten state itself. So there is a no gaseous state. That is the concept. Here, at very high temperature, in a metal alloy system, it will be exist as liquid phase or molten state only. It will not be converted into gaseous state. So if there is a no gaseous state, we can neglect the term pressure. We can neglect the term pressure. So if the pressure is negligible from this formula, it will become F equal to C minus P plus 1. And this is a called reduced phase rule. F equal to C minus P plus 2 means normal phase rule, that is a regular phase rule. F equal to C minus P plus 1 means that is a reduced phase rule. And this formula is applicable for all metal alloy system. This is applicable for all metal alloy system, which we are going to discuss now. So now we will have a clear idea about the terms. So just I have gave a brief introduction about these terms. Then only you can easily understand the lead silver system. Now I will move to the explaining the two component system, that is a lead silver system. The title is two component, that is a lead silver system. So I'll draw the diagram and I'll explain. Draw the diagram here. Okay. First I will label the diagram, then I will start explaining. In an x-axis, it is a temperature. Temperature in a x-axis. y-axis it is a composition, it is a composition, and the temperature of at this level is 303 degrees Celsius. It is a 303 degrees centigrade. Now we will label the curves. So it may be considered as a point O. This is a point O, and this may be the A, point A. So this is the point A, and this one is a point B. Now we have labeled point O, point B, point A. So I have drawn the two curves. The first curve is OA. This is the first curve, big curve. And the second curve is OB. First curve is OA and second curve is OB. Actually, this curve represents the freezing point curve of silver. Freezing point curve of silver. So what is the freezing point? What is the melting point of silver is? If the silver is heated at very high temperature, it will be converted into molten state at 961 degrees Celsius. When it will be converted? It will be converted into 961 degrees Celsius. So the freezing point of silver is 961 degrees centigrade. At 327 degrees centigrade, here that is a point. The point B, it is a 327 degrees centigrade. So at 327 degrees centigrade, the lead will be converted into the molten state. Now we'll see at this point. So at this point, at the initial point, the lead is present 100%. The lead is present 100%, and the composition of silver is 0. Initially, we are taking 100% of lead and 0%. There is no presence of silver at this point. When you move from here to there, while moving here to there, the composition of lead is getting decreases and silver is getting increases. When you move from here to there, the composition of lead is getting decreases and the silver is getting increases. What will happen? At the final stage, at one stage, the concentration of lead will become 0. At this final stage, at this point, the concentration of silver lead becomes 0 and the silver is 100%. So this is how the composition is vary from here to that. This is how the composition is vary from here to that. So at this point, it having 97.4% of lead and 2.6% of silver. Usually, student will do one common mistake while drawing the phase diagram in the examination. What they will do? Simply they will draw the square and everyone they will do as a perfect 303 degrees centigrade. See here, what is the freezing point of lead? 327. Here it is at 961. See the range of x-axis 327. Then higher temperature is for silver. 327 is a lower temperature and the higher temperature is for silver. So the point you need to start from B. This one should be in a lower. In x-axis it should be the less, and then you need to very big axis, higher range for the silver. Usually a student what they will do? So they will like in a both OA and OB curve. So they will like in same range in a y-axis. So that will be a wrong representation. So here one curve should be the small and it should start from the lower temperature. Another curve should be the big and it having the higher temperature because it is a 961 degrees centigrade and this is a 327 degrees centigrade. So this is a less, this one is a high. Likewise, you need to draw the curve. This is an important thing, you need to keep it in your mind. Now we'll move on explaining these curves. How the phase rule is applicable and all the things. Before that, I will label the curves. I'll label the curves and what are the things present inside. I'll explain all these things and I'll start moving to okay. So this is a freezing point curve of a lead. So here, what are the things present? Lead is present with eutectic. Lead plus eutectic. Now the question may arise, sir, what is meant by eutectic? I will tell. Here, silver, sorry, here it is a lead plus liquid melt. Here, silver plus liquid melt. Before the 303 degrees centigrade, it will exist as a eutectic. What is eutectic? It is a low melting temperature. For example, just imagine if your mother is want to heat the ghee in the kadai, means when you put a solid ghee in the kadai, initially after putting the ghee into the solid kadai, initially it start to melt. It will not be completely melted at the first second, so it start to melt. So the low melting temperature, it will start to melt, but it will exist as a solid phase only. That temperature is called eutectic. So at this stage, at this area, it will exist as lead solid plus eutectic. Here it will be exist as solid silver plus eutectic. So we can mention it as a simply lead, or we can mention it as a solid lead. We can mention it as a solid lead. In all the places we can mention it as a solid. Here also it is a solid. So carefully listen. Before 303 in a less than 303 degrees centigrade, it will exist as a solid material plus eutectic. So this is the area for lead. So at this stage, at this area, it is existing as solid lead and eutectic. Here it is existing as solid silver plus eutectic. After the 303 centigrade, it has started melting. So the mixture of liquid and solid. Here the mixture of liquid and solid. What is the things present here? Solid lead and liquid. Here solid silver and liquid. So these are the things present here. Now, what is the thing present here? Here, after 327, above the 327 degrees centigrade, the lead is converted into liquid melt. Above the 961 degrees centigrade, the silver also converted into liquid melt. So in this area, it possesses only the liquid. Both lead and silver will be converted into the liquid melt. So this is a clear description of this diagram. If you understand the diagram clearly, it is easy to find out the number of degrees of freedom for a particular area at a particular curve or a triple point, whatever it is. So all the informations I have mentioned in the diagram. All the informations. What is the freezing point of lead? What is the freezing point of silver? And another thing we need to mention here. We can name the curve. How can you name the curve? So there are two curves present here. One is a OA curve, another one is a OB curve. So this curve is called freezing point curve of silver, because at this stage silver is converted into the liquid melt. So this curve is called freezing point curve of silver. Freezing point curve of silver. And this curve is called freezing point curve of a lead. So this curve is called freezing point curve of lead. So now all the informations are clearly given in the diagram. So now our job is simple. The job is simplified. So now we need to explain the terms which is present in the diagram. The three things I am going to explain in the diagram. The one is curves. One is curves. There are already, as I told, there are two curves present here. One is OA curve. This curve is, this is a point O and this is a point B, sorry, is a point A. So OA curve. In a curves, the first thing is OA curve. Another curve is also here. This is the curve. OB curve. This is a point O, this is a point B, OB curve. The second one is OB curve. So there are only two curves. And another thing is the point O. This is called eutectic point. The point O is called eutectic point. Eutectic point. So I need to explain I'm going to explain the eutectic point. And one more thing is that areas. We can separate into three different areas. This is the one area, the area which contains the liquid melt. This is the second area, the area which contains the solid silver and liquid. This is the third area, the area which contains the solid silver and liquid. Once again, I will tell. This is the area which contains the liquid melt. Area 2, which contains the solid silver and liquid. Area 3, which contains the solid silver and liquid. So these three areas I am going to explain. So areas, the third thing. Areas, three area. How can we name the area? So for a curve, simply I have named it as a OB, OA I have named. So three areas we need to name. The first area is the area which contains a liquid. So we can name it as, the point 1 is a B, second point is O, third point is a A. So we can name it as BOA or we can label it as AOB. The area AOB. Area AOB which contains a liquid. This is the first area. And the second area. So we can represent it by below the line AOB. So this is the line above the AOB. And AOB means AOB. And this is the area above the AOB. Simply we can change it as above AOB. So below the AOB, below this line, it has two different areas. Okay. So below AOB, area 1, below AOB, area 2. So above the AOB, only liquid is there. Only liquid is present. Below AOB, there are two areas. The first area contains a solid lead plus liquid melt. The second area contains solid silver with the liquid melt. So these things I am going to explain. For these things, we are going to see the determination of a phase rule. Let me start one by one. So I'll start with the curves. The first one is AOB. Sorry, OA curve. OA curve. Now I will write the equilibrium reaction existing in OA curve. The equilibrium reaction existing in OA curve. See, The OA curve separates the liquid and the solid AG. The OA curve separates the liquid and solid AG. So at any point of the OA curve, the equilibrium is existing between the solid AG with the liquid. So at any point of the OA curve, the equilibrium is existing between the solid AG with the liquid. Now we need to find out the number of degrees of freedom. It is very important to remember this is a two component system, and this is an example of a metal alloy system. In the case of metal alloy system, we need to apply the reduced phase rule. In the case of reduced phase rule, the pressure will be negligible, so the phase rule become reduced phase rule. The formula is F dash or F equal to C minus P plus 1. Now it is our duty to find out the number of component phases in this equilibrium. What are the things? F dash is equal to number of component. Component 1, solid silver. This is the one. So this is the one component. What is the second component? Only liquid is there. What are the present in a liquid? See the diagram. Above the 327 degree here, above the 961 degree centigrade there. So above this, both silver and lead will be converted into liquid. So the liquid melt contains both solid and liquid. So the number of component is 2. Number of phase, solid and liquid. Here the first phase and it's the second phase. 2 plus 1. So 2 minus 2 plus 1. So F dash is equal to 1. So system is univariant. F dash is equal to 1. So the system, which means this equilibrium system is univariant. This is for a first OA curve. And the second curve is this is the second one. OB curve. The second one is OB curve. See the diagram and tell me where the OB curve is there. Is a O, point O is a point B. So this curve is named as OB curve, which is a freezing point curve of lead. So in this curve, at this any point of the curve, the equilibrium is existing between the solid lead and the liquid melt. See, at any point of the OB curve, the equilibrium is existing between the solid lead and liquid melt. So the equilibrium reaction is between solid lead with a liquid melt or liquid. Now we need to do the same process. By applying reduced phase rule, we need to find out the number of degrees of freedom. F dash is equal to C minus P plus 1. So F dash is equal to the number of components. As I told earlier, here also the first component is a lead, second component is silver. Where is the silver present? The silver is present mixed with the liquid. The liquid contains the both lead and silver. So the component is 2, the phase is solid, liquid. Phase number 1, phase number 2. Plus 1 and F dash is equal to 1. Here also the system is univariant. So the part curve is over. Here this is at any point of the OA curve, the system is univariant. At any point of the OB curve, the system is univariant. Now we'll move to the eutectic point. The point O in the diagram, see this is the point. This is the point. The point O is called eutectic point. Let's imagine, I'll give 30 seconds. What may be the equilibrium in point O? Just to see the diagram and imagine what may be the equilibrium reactions in point O. Equilibrium reaction, what is existing in point O? Equilibrium reaction which is existing in eutectic point. So number 2 is eutectic point or point O, eutectic point, 0.2. So this is a technique point. So this point connects the liquid. This point connects the solid lead. This point connects the solid silver. So at this point, there is an equilibrium between both the solid states with the liquid melt. At this point, there is an equilibrium between both the solid states. So what are the solid states? Solid silver and solid lead. So solid silver, solid lead plus solid silver is equilibrium with liquid. Solid lead, solid silver is equilibrium with the lead. So this is a equilibrium reaction is existing at this point. Now the procedure is the same. We need to find out the number of degrees of freedom for this equilibrium reaction. So again, you need to keep in your mind, it is a reduced phase rule formula, that is F dash is equal to C minus P plus 2, sorry, P plus 1. If it is a 2, it is not reduced phase rule. One is reduced phase rule. How many components present here? The concept is simple. Don't bother whether how many phases are present. If it is a liquid there, because only we are taking the two components, title itself, lead silver system. The title itself, the having a name, lead silver system. So automatically wherever the liquid comes, the liquid possesses both lead and silver as the components. So the no doubt, the number of component is 2. Now we need to find out the phases. How many number of phases? Liquid, solid. How many is it? 2. Both are solids and this one is a liquid. What is the number of phases present here? Earlier I already told, if 2 different solids are there means you need to consider 2 different phases. So solids are immiscible in a normal room temperature. So 2 different solids, solid 1, silver, phase number 1, sorry, lead, solid 2, silver, phase number 2, and third one liquid. So 3 different phases are here. So the answer is 0, which means the number of degrees of freedom is 0 and the system is represented as non-variant. The system is represented as non-variant. Now this point is also over. This part is also over. And now we are going to discuss about the area. There are 2 parts, area above AOB line, this is the area, and below AOB it having 2 areas. One is which contains a solid lead and liquid, another one solid silver and liquid. The third part, area above AOB. Area above AOB. What is the thing present in above AOB? This is the area. AOB. And this is a part existing in above AOB. At above AOB, what is the equilibrium? See, only one phase is present here. Only one phase is present here. There is a no equilibrium reaction. Only one phase is existing above AOB. That is a liquid phase. Only liquid is present. There is a no equilibrium reaction. Now we need to write the reduced phase rule. The number of degrees of freedom for this area, that is F dash is equal to C minus P plus 1. What is the number of component here? It is a title itself, it having the answer, lead silver system. There are 2 components, even the phase is 1. Both lead and silver is melted and it will be converted into the liquid. So the number of components are 2. The number of phase, only one phase, that is the liquid. Phase is 1 plus 1. Sorry, F equal to 2 minus 1 plus 1. The answer is 2. The system is bivariant. the system is bivariant. Now we are having a two more area. The one is below AOB. The first one is the area which contains a solid lead plus liquid. And the second area, this is area number 1, this is area number 2, the area number 3 is below AOB, which contains solid lead with the liquid. So the discussion for these two area, these two separate area is a common. So I have mentioned is a single discussion. The same thing we need to find out. F dash is equal to C minus P plus 1. Or we can discuss it separately. First I will discuss about the second one. This is for a first one. Again I will discuss the third one. We will take the second one, below AOB, which having a solid lead and liquid. Where it is in diagram? See, this is the area. This area which contains solid lead and liquid. Solid lead and liquid. For this area, we need to find out the number of degrees of freedom. So F dash is equal to the number of components. What is the equilibrium? Before that, we need to write the equilibrium present here. At this area, the equilibrium is existing between solid lead with the liquid. The equilibrium is existing between solid lead and liquid. So at this point, we need to find this area, we need to find out the number of degrees of freedom. So F dash is equal to how many components present here? It's a common thing. It's a 2. How many phases present here? Phase 1 is a solid, phase 2 is a liquid. Because only there are 2 different components. Phase 1 is a solid. So F equal to 2 minus 2 plus 1. The answer is 1. And the system is univariant. The system is univariant. See, both are the areas. In above AOB, the system is bivariant. The below AOB, the system is univariant. Above AOB, it is a bivariant. Below AOB area, it is a univariant. The same thing we need to calculate for the another area. That is a solid silver with a liquid. The same formula. Before that, you need to write the equilibrium reaction. Here, the solid silver is equilibrium with the liquid. The solid silver is equilibrium with the liquid. And the same thing, F dash is equal to C minus P plus 1. So F dash is equal to the number of components are 2. One is a silver, another is a lead which is mixed with the liquid. That is a 2. The phases are 2. One is a solid, another one is a liquid. Plus 1. The answer is 1 and the system is univariant. The system is univariant. Now I have explained all the things present in the diagram, which are curves. There are 2 different curves, OA curve, OB curve. And we have discussed, we have determined the number of degrees of freedom of OA and OB curve. And then we have discussed the eutectic point. Eutectic means a low melting temperature. So at the eutectic point, we have determined the number of degrees of freedom. Then we have moved on the areas. We have separated it as a 2 different areas. The first area is above AOB, second area below AOB. Above AOB, it is having a single phase, a single area. Below AOB, we have again separated into the 2 areas. So for all these things, so we have determined the number of degrees of freedom. So I have left with one more point. See, I have drawn one dotted line here. I didn't discuss about this dotted line. Now I will name this dotted line as this may be the point P and this may be the point Q. What is the point P and Q, sir? So now I am going to explain the application of lead silver system. The application of lead silver system is explained by means of a Pattinson's process. Pattinson's process means desilverization of argentoferrous lead. Desilverization of argentoferrous lead, which is called I will write it, Pattinson's process. Application. Application of lead silver system, that is explained by using Pattinson's process. Pattinson's process. Pattinson's process is a desilverization of argentoferrous lead. Desilverization of argentoferrous lead. It is a known thing. The cost of silver is high. Nowadays, the 1 gram of silver is nearly around 270 rupees as of now. 1 gram of silver is at 270 rupees. So, if you want to working the lead and silver means, so we need to buy the silver. So, we need to buy the costly material to determine the phase system of this diagram. So, we need to work with the costly materials. So, if you are working with a costly material means, if possible, it has to be recovered. It has to be regenerated. So, by using this process, the valuable or the very costly silver is getting recoverable. So, that is called desilverization of argentoferrous lead. Now, I will explain how it is possible using this diagram, how it can be possible and how it is done. See, at the point P. At the point P, so the percentage of silver is low and the percentage of lead is high, as I mentioned here. At the point P, the percentage of silver is low, the percentage of lead is high. While reducing the temperature, when you move from point P to Q, while reducing the temperature, the lead is start crystallizing. While reducing the temperature, the lead is start crystallizing. So, the crystallized lead is frequently removed from the mixture. And you move from top to bottom and you move from the P to Q. Initially, the lead is start crystallizing. So, the crystallized lead is removed. So, that argentoferrous lead is removed. So, the remaining solution having a more concentration of silver. So, the high cost silver is recovered by this process. This process is called Pattinson's process, which is desilverization of argentoferrous lead. So, this is about a lead silver system. So, now I can conclude this lecture. So, what are the things? So, we have discussed and all the things I will conclude in another couple of minutes. So, initially we have started with the basic terms, little bit elaborated, because to understand the lead silver system, you should strong about the concepts present, what are the terms involved in the lead silver system. So, for that I have explained the important terms. What are the terms? Just to recall, we have discussed about the phase, component, number of degrees of freedom, phase rule and reduced phase rule. So, these basic terms I have explained with simple examples. For understanding, I have explained with a simple example, and we move to the diagram part. And it is again, I will insist this one. In a diagram itself, we need to mention all the information, because in case if the question will ask in a 16 mark means, so you will get a 6 to 7 mark for diagram alone. So, if you the 6 to 7 mark will be provided for diagram means you need to mention all the information in the diagram. So, we have I have explained the diagram. in a diagram itself, I have mentioned all the informations. What is the temperature of melting, freezing point of a lead? What is the freezing point of a silver? And I have labeled the curve. And what is the name of the curve? And what are the things present in x-axis? What are the things present in a y-axis? And what are the composition present in that particular area? What are the things present above AOB? What are the things present below AOB? All the informations you need to include, you need to provide in a diagram. Then it is a very simple to explain the diagram. If you mention all the things in the diagram means, so you can easily explain the curves, eutectic point and areas. So after the diagram, so three concepts we have explained. We have taken the three concepts. Concept one is a curve. There are two curves present here, OA and OB curve that we have discussed. Point number two, eutectic point. The point O is called eutectic point. That's a low melting temperature point. The third one is the area. We have separated it to two, above AOB, below AOB. Again, below AOB, it having two different areas. So totally three areas we have discussed. So this is about the lead silver system. Thank you. I'll stop now.